Welcome back, Chemistry 30. So we started to look at hydrogen bonding here. When hydrogen is bonded to a very high electronegative F, O, or N, we get something referred to as hydrogen bonding. So that high electronegative atom, whether it's an F, O, or N, pulls the electron to its area more often, making it very, very negative here and very positive here, because all that's left is that positive, that proton in hydrogen's nucleus, since its electron is in the other area most of the time. Now that high electron poor hydrogen is so small it can approach an electronegative atom very closely and interact strongly with it. Also, when hydrogen is bonded to one of these very electronegative elements, such as an F, O, or N, the hydrogen nucleus is exposed, as I mentioned. Hydrogen bonding is often responsible for the unique characteristics of water, in that solid ice is less dense than liquid water. So we talked a bit about this in physical science. So if I have a O and my H's here, oops, let's make this a little bit better here. So if I look over here, O and H, O and H. So in a liquid, they're moving around, and they don't have a chance to be really attracted to each other and have that hydrogen bonding take effect. But if they slow down enough, oh yes, this H is attracted to the lone pair of electrons in this O, and so on and so forth. And you can see it makes a hexagon type structure, which is less. So the solid, now this isn't a solid piece, so it's slowed down enough so that hydrogen bonding takes effect, and we get a hexagonal structure in ice, which is less dense than the liquid form. And I think water is the only substance that does that due to that hydrogen bonding. So when water freezes, water molecules slow down enough so that hydrogen bonding can occur to a great extent. The above structures occur, the above structure occurs in the solid form of water. The form of this is less dense than that of the liquid form, due to the molecules being relatively spread apart. So you can see they're really spread out in making this structure, whereas in water they would be very close to each other. In the liquid form, hydrogen bonding is more random, and the above structure will not occur due to the motion of water molecules being so much faster than they would be if they were solid. The resulting liquid water molecules will be closer together than in the solid form, because usually in a solid, atoms are close to each other and they become more dense, because usually this is how we kind of describe it. So we have a solid very close to each other, really dense. In a liquid, further apart. And of course in a gas, yes, floating around and really far apart. So that's a relatively interesting thing about hydrogen and oxygen in water. The last force we'll look at here is ion dipole, and kind of the words there tell us what it really is. It's an ion in a dissolved compound attracted to a dipole of some other molecule. So these are important in solutions that contain dissolved ions. So the strength of these forces is what makes it possible for ionic substances such as salt, sodium chloride, to dissolve in polar solvents such as water. So over here we have water, so we drew the molecule of water like this. So O, H, H. And then we have chloride ions and sodium ions. So when you dissolve salt in water, you get chloride ions and sodium ions. So what happens here is that, and of course, the O is negative, the H's are H's, the H atoms or ions are positive. So positive and negative attraction. So you can see the H attracts the Cl. H attracts the Cl, H attracts the Cl, etc. Whereas the negative O attracts the sodium. So negative O attracts the sodium. So water molecules surround. Now sodium chloride would look like this. It's a big lattice structure. Sodium and chlorides and sodium and chlorides and sodium and chlorides. But the water molecules come close to it and pull it apart. So the H's attract the chlorides, and then a bunch of water molecules surround a chloride ion, and the negative O's of the water surround the sodium ions. So we have something that we can actually see to something that we can't see because they are simply too small. So we can take a look at a summary here. So do we have ions present? If we do, are they polar molecules? Then it could be ion dipole. So ions attracted to neighboring water molecules. If they aren't molecules, then we're talking about sodium chloride, calcium chloride. So any ionic solid that will have ionic bonding, and that's considered pretty strong. Now, if I don't have ions present, are they molecules? Yes. Are they polar molecules? No. Then we just simply have dispersion forces, such as between nonpolar methanes or nonpolar polar bromides. But if they are polar, does it contain H bonded to an N, O, or F? If yes, then it's going to be hydrogen bonding. If not, then it's not hydrogen bonding, but it is still a dipole. Then we can think of it when moving from left to right. If we have a molecule like this, it's simply dispersion. But remember, everything has dispersion forces. So a dipole, it would have dispersion forces as well because there's random electron movements with everything. If I have hydrogen bonding, guess what? Hydrogen bonding is a form of dipole, and it also has dispersion forces. And we can see it increases in strength as we go from left to right. So multiple types of intermolecular forces could be work in a given substance or mixture. In particular, as I mentioned, dispersion forces occurs in everything. Intermolecular forces affect many physical properties such as boiling point, melting points, etc. And the strength of the attractions between particles can greatly affect the properties of that substance in a solution and in general. So you also have this sheet on the end, which is kind of a summary sheet of all the four intermolecular forces, starting off with London dispersion forces. So again, we have attractive forces between any two molecules. So any molecule can attract another molecule, and of course that's by random electron movement. We could have electrons collect there, which means this side's going to be positive, and that'll cause all the electrons in this to go to the opposite side, leaving us with positive behind. Okay, dipole. So again, London dispersion happens with anything. Dipole, they have to be two polar molecules. So a permanent dipole. So it's permanently negative, permanently positive, permanently negative, permanently positive, and the opposites attract here. Notice that the arrow shows the direction of the electron movement when they're shared. It's always towards the more electronegative one, which will be negative, and that kind of leaves a positive behind. So that's the attracting force. And then, of course, hydrogen bonding is a special type of dipole. It's the electrostatic attractive force between the partial positive charge hydrogen in one end of a FO or N molecule, FO or N, and the negative charge lone pair of a negative FO or N, which does not have to have hydrogen. Does not require H bonded to an F or N. It just simply has to be an F or N. So we have your FO or N, we have their lone pairs of electrons. This positive H will be attracted to that negative area of that neighboring molecule. Okay, and of course I showed quite a few examples here. Ones that were in fact bonded to F or N. Let me see if I can get that sheet again. Here it is right here. So as an example, now you could have H bonded to an F over here, and that H will be attracted to a neighboring F or N. That F or N does not have to be bonded to an H though. In this case, in this particular example, it is, but it doesn't have to be. So that positive H is bonded to that lone pair, which is going to be very negative on a neighboring F, O, or N. So that's how hydrogen bonding works. Then the last one here, ion dipole. The electrostatic attractive forces between a dipole and an ion, or a formal charge. So you have your dipole. A lot of the time the dipole is a polar molecule such as water, and it's going to attract to an ion that's dissolved in solution. Because you remember, if you dissolve sodium chloride, we have positive sodiums and negative chlorides. So the positive end of a polar molecule will surround and attack a negative ion. Or the negative part of a polar molecule will be attracted to the positive end, the positive cation. So that's a summary of all four of those dispersion forces. We'll call it quits there, and when we come back, we'll go through some of the rest of the assignment, and I'll give you some hints in terms of how you tackle some of the questions.